All right, Blake, it's all yours.
Okay. Welcome, everybody. Can everyone see it on Zoom?
Yep, we got it on Zoom.
Okay, great. So, yeah, as we said in the introduction, we're taking a little bit of a left turn. We're still sticking with marine vertebrates, but we're looking at an extinct vertebrate called Hesperornis. Yeah, sorry. For my study, I'm specifically interested in the ecological controls, the biological and environmental impacts that could be driving the distribution of Hesperornis. And I'm going to be doing this using a modeling technique called species distribution modeling, which I will be getting into in just a few minutes here. So first, a little background. As some of the other talks have said, we have the Lake Cretaceous being a hothouse environment where sea levels are much higher. That, combined with some tectonic activity, enabled the formation of the Western Interior Seaway. This relatively shallow body of water connected the high Arctic with what is now the Gulf of Mexico. For my talk, I'm focusing on the Campanian period of about 11.5 million years within the Western Interior Seaway. So just for comparison, the Seaway open around here and retreat and close somewhere in the Maastrichtian. The exact closure point is a little bit debated, but one thing to keep in mind with this presentation is I'm talking about North America during the Campanian, so it's not in its current position. Relative to today, we can see if we look at this 150-degree longitude line, North America has shifted well over to the east. It's also moved slightly north and rotated. So the Western Interior Seaway was full of a number of creatures that we've seen thus far, including our favorites are marine reptiles, number of cephalopods, bony fishes, cartilaginous fish, pterosaurs, and Hesperornithiformes. He's just chilling up here on the top. So Hesperornithiformes specifically, they are flightless diving birds that bore teeth in their jaws. These guys were foot-propelled pursuit divers, kind of like you see with ducks and cormorants today, unlike penguins who essentially just flap through the water. Among the Hesperornithiformes, Hesperornis is the most abundant member of the group. Their fossils are known all the way across the Western Interior Seaway from Arkansas into the high Arctic regions, primarily from marine sites, but also from some fluvial and estuarine deposits. Hesperornis bones tend to fossilize a little bit better than some other avians, just because they have several parts of their skeleton that are more robust for this foot-propelled diving lifestyle. Specifically, the hind limb, as well as the pelvis and vertebrae. Now, I should also say Hesperornithiformes are thought to be generalist feeders, feeding on cephalopods, crustaceans, as well as fish. And we'll see. So they're thought to be most similar in hind limb morphology to cormorants, of which today a good analogy is the flightless cormorant from the Galapagos. So while their hind limb morphology might be similar, the two groups are not closely related. Let's see if we can get this to play here. So just imagine Hesperornis coming around. They're There we go. Oh, wow, that figure did not show up. So now we're transitioning a little bit to talk about the models that I'm using to make inferences about the distribution of Hesperornis. So species distribution models, or as you might see them in the literature as SDMs, and they have a number of other names that have been debated over, but that's a topic for another time. They use abundance or occurrence data where the species have been found at sites to, well, in combination with environmental and biological information to make these inferences about their distribution. In this example here, Myers et al., well, this is, yeah, anyways, in this example here, the occurrence data are represented by these pluses where this crinoid has been observed in comparison to the environmental information, the blue diamonds, to create a map of the most suitable habitat or where it's most likely to be present, with dark blue in this example being the least suitable and orange and yellow being the most suitable. Now, most paleontological SDMs have focused on non-marine taxa as well as benthic or bottom-dwelling invertebrates, with only 2 studies including marine vertebrates, one of which looked at the past distribution of the extant Atlantic cod, and another looking at the extinction of our good old friend, the Otodus megalodon, which this figure is a little messed up, but they were essentially showing that the climatic conditions going up past its extinction and by the Pliocene were maintained all the way up to the present. So it's likely another driver was the cause of the extinction. So I'm specifically looking at 2 types of SDMs, our generalized linear models or GLMs and occupancy models. Both of these use presence and absence data. So sites where they've been noted to have been found and not been found specifically. They differ in that the generalized linear models can use sites that were only sampled once versus occupancy models that require some information on sites being sampled repeatedly. Both of these are used to make the estimates of the probability of presence or occupancy. But occupancy models can also distinguish between true absences and the probability that a species was just not found when it actually would have been present in that environment. So this enables occupancy models to be better at estimating presence overall. But there tend to be, well, paleontological sites, at least individually, tend to be fewer in number that have been sampled repeatedly or have been noted as being sampled across repeated seasons. But generalized linear models, on the other hand, since they only require sites to be sampled once, there's a larger sample size. So I'm comparing the 2 in order to see where they agree. So my data set includes 61 localities across the Seaway, including 26 bearing Hesperornis, as noted by these orange triangles. I collected a lot of this information from online sources, but I also visited a few institutions to gather some data on occurrence information, as well as stratigraphy. I ended up including 24 taxonomic variables from different levels of clades, including genera. Then I also used some environmental and geographical variables, including 3 types of rocks, just more as a little bit of proxy for the environment. I also used Paleolatitude, just set at 80 million years. west-east position in the western tier of Seaway, since longitude would not account for the curvature of the Seaway, and outcrop area just as a general proxy for the amounts of rock to be sampled, though there are issues that it's not a direct correlate to exposure area. So the models I created for the generalized linear models in R have a sample of the code up here. I created two types of generalized linear models, one using all 61 localities and another using 22 localities that had been sampled repeatedly. Now, I will say some of these localities are actually representing combined sites. Just for these purposes, I was combining sites that fell within about 10 kilometers or so of each other. Though this site buffer can be tested and should be tested in the future. Then for the occupancy models, I created these in presence using those same 22 areas that have been repeated, have a lot of sampling. Hesperornis is present at half of them, have a couple of the windows of the program presence here. Okay, so all that aside, the results are showing that there's a number of repeating assemblages of variables, but I'm specifically focusing on where the model types agree since they have a little bit different sources of information. For today's talk, I'm going to be focusing on where they all agree in that Elasmosaurus and Paleolatitude had some form of influence. So Elasmosaurus themselves are a long group of long-necked plesiosaurs reaching about 12 to 14 meters in body length at a maximum. But they have heads that are only about half a meter to 0.6 meters in length. These are just a few examples of some Campanian species in the Seaway. Now, all the models were including Elasmosaurus as a biological factor that decreased the probability of presence for Hesperornis. This could possibly be related to competition in some respects. And here's, I'm going to show some evidence that could be in favor of this hypothesis. So the Elasmosaurus and Hesperornis are they're found in offshore marine, shallow marine, and non-marine sites, with the non-marine sites being concentrated more in this region here. The distribution of sites on this map with the red stars showing the Elasmosaur occurrences in the current data set and Hesperornis occurrences with the triangles shows that they're occupying the similar environments, but typically separately. In addition, in the largest Elasmosaur, the Elasmodon, though I will say this one is probably more representative of a type of Styxosaurus, as we saw earlier. But in Elasmodon, there was a estimated gap across the throat of about 15 to 18 centimeters. And with this one being the largest Elasmosaur, all the other adults, as well as any juveniles, would have a smaller spacing. This small width of the throat, as well as small head length, overall rigid skulls, unlike what we've seen with mosasaurs, as well as slender teeth, are going to be limiting the size and type of prey. So the negative influence they have over Hesperornis as predicted by the models is likely not predative, just because with the larger Hesperornis species, which could reach up to 2 meters in length, so approaching my height, those would not be consumable, though it is possible some of the smaller Hesperornis, which could get to about 0.8 meters, could have been eaten, but so far the evidence is against it. Some other evidence in favor of the competition hypothesis is that there's dietary overlap with Elasmosaurus and Hesperornis, and that Elasmosaurus are also known to have fed on fish, crustaceans, and cephalopods as well. And muscle models are suggesting more of a rapid snapping motion rather than trying to bite and tear on harder bony animals. Moving on to Paleolatitude. The Paleolatitude is predicted by the models to increase the probability of presence for Hesperornis. In the current literature, this relationship has been attributed to migration in some form, though the exact reasons for the migration are currently unknown and have been discussed. So the results here are adding more of a quantitative assessment, but some of the other work that has been done has shown that described specimens of Hesperornis that are juveniles and subadults are only known from southern Manitoba and southern Canada up to the high Arctic. This has been hypothesized to be migration for breeding purposes. In addition, the highest abundance of Hesperornis tends to be between southern South Dakota and Saskatchewan. Now, this seems to be indicating another connection to Paleolatitude, but the exact reasoning is unclear. Perhaps some of them might have died during migration and when they're coming through mid-latitudes, but that is currently unknown. There's also evidence suggesting that Hesperornithiformes and just seabirds in general are more restricted to higher abundance in cooler waters going north. So just to sum things up, the strongest ecological controls are Elasmosaurus, possibly due to competition, and Paleolatitude for migration. There's other explorable controls as well, where you have 2 model types agreeing versus all 3, including mosasaurs are reef and bony fish and carbonate rocks. SDMs are offering a quantitative insight for ecological patterns. I have quite a few people I'd like to thank, including my funding sources, thesis committee, all those that provided access to collections as well as information. I know I've had a number of email chains going and trying to figure out where specimens were and what was in the area, as well as a few others that have helped me along the way. But before I leave, I just want to jump back a few 100 million years to give you guys an ichthyosaur fact. So in the late Triassic, there was an evolutionary bottleneck where we saw a restriction in the overall disparity of ichthyosaurs. So by the beginning of the late Triassic, we see the disappearance of the basal and more eel or lizard-like forms. And we see our last of our intermediates during the late Triassic, all in favor of the typical fish or dolphin-like ichthyosaur that we're used to. And this body morphology is maintained throughout the rest of their existence to the late Cretaceous. And with that, I'd be happy to take any questions.